Okay, let's get started. Welcome to the SNAPP seminar. For those who joined a little bit later, just to let you know, we are recording this Zoom seminar. So if you don't want to be recorded, you can watch the YouTube live as well. As a reminder, please, a couple announcements, please mute yourself during the talk, but please keep your video on so that Sujay can see who he is presenting to as well. And so the talks are recorded and the slides are posted on the website, and I'll put the link in the chat box soon, so you can also follow along. So today we're pretty excited to have Sujay Sanghavi join us and present on towards model agnostic robustness. Sujay is an associate professor at University of Texas, Austin. His research focuses on rigorous methodological innovation in machine learning using ideas from optimization, statistics, and graph theory. And he has received early career awards from NSF and DoD, and currently leads the NSF Tripods Institute on the foundations of data science at UT. He is also currently a principal research scientist at Amazon. So take it away. Oh, sorry, one more announcement I forgot to mention. Sorry. So about how we're handling questions. If you have any clarification questions during the talk, please write them in the chat box. I'll be monitoring the chat box, and we will take clarification questions as they come. However, if you have any longer questions, then we'll take the questions during a pause in the middle of the talk and then a longer Q&A section at the end of the talk. All right. Take it away, Sujay.
Okay, can everybody hear me? Yeah. So I really want to thank the organizers of the SNAPP seminar for inviting me. Yeah, so I mean, I hope to keep it reasonably interactive. So please feel free to ask questions, and I'll also stop at various points and see if there are any clarifications. A pretty simple talk with a simple idea. So okay, let's get started. So the title of my talk is towards model agnostic robustness, but specifically using a very simple idea, which is sample selection. So let me just briefly introduce the background and the motivation, and then also what it is that we're doing. So as everybody knows, a lot of the modern success and interest in machine learning has been driven by larger and larger machine learning models trained with more and more data, right? So kind of this combination of having a bigger model and a lot of data usually gives higher accuracy on various tasks, but specifically, there has been a lot of success in language understanding, computer vision, and kind of the intersection of the two. So while this is great, they're also harder to train and design from. It's becoming harder and harder to design machine learning models and also to train them from scratch, right? So you need lots of compute, you need lots of data. And the choice of architecture is a little bit of an art and not a science. I think it's fair to say. So there are several issues that come up, and the ones that we will focus on in this talk have to do with robustness. So specifically, we're going to talk about robustness that comes from errors in labels, right? Or from sloppiness in data set collection. There is a different meaning of the word robustness, which has to do with an adversary, kind of adversarially changing your data. We are not going to talk about that kind of robustness. We are talking about robustness that just comes from, 20% of your labels are wrong or something like that, right? But not that you're changing like individual pixels or individual words, in an adversarial way. So that briefly is the background. So what I'm going to present today is what I like to think of as a pretty generic approach to getting robustness. By generic, I mean that it's somewhat independent of the specific model you're trying to train and your specific data set, right? So just to set it up, this is the typical flow of, or this is like a kind of black box diagram of how a machine learning model is trained, which is that, you have a training data set from which you can have a sample selector to get a batch of training samples, which you then use to update the parameters of your model, which you then use to make a loss function, and then use a gradient or something on that loss function to update your model parameters. Okay. So what we are going to do is so this is pretty generic, like almost any machine learning model is trained in this kind of high level way. And what we're going to do is we're going to make two kinds of changes to this. Right? So I think of it as like an inner loop and an outer loop. Right. So this workflow of training data set to model parameters keeps happening again and again, easily in epochs and iterations. And so what we're going to do is two different things, right? So one is what I like to think of as the outer loop, which is that we'll do one round of model training, then we will change the training data set. Okay. And then we will do it again. And then we will change the training data set and do it again. Right. So if you can think of standard model training as one round of this, we will do multiple rounds, each time focusing in on a different subset of the training set. Okay. And this will become clearer as I go further. Another style of algorithm change that we will look at is what I think of as an inner loop, where we have a training data set, but then it typically iteratively select samples and update parameters, but we will change how we do the sample selection in every time. Right? So if you think of something like stochastic gradient descent, right? The sample selector at every time chooses a random set of samples, makes a batch, updates model. Right? So instead of that, we will change how this sample selection happens. Right? So that I think of as like an inner loop. All right, so let's try to give a little bit more specific motivation. Right? So here's a pretty typical thing that many grad students do when they start looking at neural nets, which is to take a pretty standard, I wouldn't say small size data set, which is CIFAR 10 from almost a decade ago. And take a pretty standard neural network architecture, which you can just nowadays just download from the web. So for example, wide ResNet 60, right? And you can train this neural net from scratch using this data set. So this is a classification task where we have images from 10 different labels. I'm sure most of you have seen CIFAR 10 before, but for those who haven't. These are a set of images, and they're from 10 classes. Right? So the first class is airplane, automobile, and so on. Right? And so this is the data set, and the typical task is given a new image, assign one of these labels to that image. And so if you take this data set, you take this neural network architecture, and you train it, you get something like 92% accuracy, right? In the 92% test accuracy, right? And I mean, obviously, this accuracy has now been made much higher for this model. We're not on the boundary of accuracy or anything. This is just to illustrate, a kind of a typical application. Okay, what happens to this if we have errors in labels? Okay, suppose the people who made CIFAR 10 were sloppy and gave wrong labels. Okay, so specifically we're going to look at what I call systematic label noise. Okay, which is that some percent, let's say 25% of one label has been made into a specific different label. Right? So for example, 25% of things that are trucks are actually labeled birds, and cars have been labeled horses or something like that. Right? So this is systematic label noise, as opposed to random label noise, right? So in random label noise, you can have your truck being labeled as something completely random from the 10 categories. Right? So that's random label noise, but we are talking about systematic label noise. Okay. Right? So if you have systematic label noise, what happens, right? So, so that's what this graph is showing. So on the x-axis, you have the size of the data set, right? So that is the number of samples you use to train your model. And on the y-axis, you have accuracy, which is the test accuracy of the resulting model in classifying the data. Right? So if 25% of my labels are corrupted, then there is a pretty big hit in accuracy. Right? There's a pretty big hit in accuracy. And this hit in accuracy is not rescued by more data. Okay? So if, for example, this was random label noise, then we would start with pretty low accuracy. But as the data set size increases, it would kind of come up here. Right? So for random label noise, you can correct it to some extent with a larger data set. Right? Now, how large the data set needs to be kind of depends on how big your model is. This is, like we are looking at a pretty small neural model. So here, while systematic label noise does have persistent error, which, independent of the size of the data set, random label noise will not happen. Okay. So the problem we are trying to address in this context, right, just to make it more specific, is if we knew a priori that we have a bad data set, okay, that 25% of the labels that we have are not to be believed, what should we do differently? Clearly, we should do something differently, right? Like this graph says something should be different, right? But the question is what, right? Because we don't know which labels are in there, right? So that's kind of, more specific question to think about as we go, for the first few slides. Okay, this is one example of bad training data. Let's take another example of bad training data, right? So this is the famous MNIST data set where, of handwritten images. And, it is a labeled data set again, in the sense that, but for our application here, we're going to think of it as just an unlabeled data set, right? So you just have a whole bunch of handwritten images given to you. And the task is to make a generative model, which means to, make a feed-forward neural net in this case, so that if you give a random 100-dimensional Gaussian, you put it through this network, and it will generate a image, and that image should look like a handwritten digit. Okay, so that's a generative model problem. It's different from before. The previous problem was a supervised learning problem of classification. This is an unsupervised problem of just, density modeling in some sense, where the density is over the space of handwritten digits. So it's some weird distribution over pixels. Okay. And yeah, so we want to train this neural net to generate these handwritten images, right? So now this is kind of a very small baby generative modeling task, right? So the question is, what happens here if some of these training samples were not actually handwritten images, but were just something else? Okay. So the reason we chose MNIST is because there is such a simple, first of all, because it's a small and popular data set. And second thing is that there is an alternative data set called Fashion MNIST, which has the, which is supposed to be like a drop-in replacement for wherever you use MNIST, right? So Fashion MNIST, it has the same number and size of images, but they are small kind of thumbnails of, jackets or purses and things like that, right? So like kind of fashion accessories. So if I have an initial data set that is 80% handwritten digits and 20% Fashion MNIST images, right? If I do what I did before, right, which is that I just train a generative model, then the resulting output looks pretty bad, right? So in the sense that, this on the right-hand side is 32 random instances that are outputs of the generative model, right? And they look pretty bad, right? Like these handwritten digits look really bad. And there are also some fashion items, but they also look very pixelated, right? So this is pretty bad output. I mean, as compared to something like this, right? So when you have a clean training data set, you can, since MNIST is a pretty easy data set, you can make a very good generative model, where the output looks quite convincing as as handwritten digits. But when you have a bad data set, that is not true anymore, right? So again, the question is, if you knew that 20% of your training data is bad, right, but you still have to generate a good generative model for the 80%, what would you do differently? Okay, so same question, but in a different context, right? Okay, so the principled approach to such a thing, obviously, is let me take a look at my ML model, right, and let me design a custom, robust variant that deals with my problem in the best possible way. For simpler ML methods like regression or PCA or so on, right? This works, like that is the approach, is the correct approach, and it works great, right? And the reason is because we understand those methods very well, and we can analyze when they go wrong, and we can fix it, right? So, however, that kind of an approach is a little bit harder to do in the context of large neural network models, because we don't even understand fully why they work even when there is no errors, right? So then trying to debug what to do when there are errors is that much harder, right? And the other thing is that the same neural architecture is often applied in many different scenarios, and so we cannot keep kind of fixing every problem that comes up. It's kind of, there is some value in having a generic approach that applies across the board, even if it may not be optimal for any of them. So that's what we'll be trying to focus on. Okay, any questions so far? Okay, cool. Yeah, so what is the idea, right? So the idea is to be model agnostic, right? And so specifically, let's look at pretty much any machine learning model, right? So our ideas apply when the following hold. So what is that? There are a bunch of parameters to the model, right? And we need to find a good value for these parameters. And the way we're going to do it is we are going to minimize a sum of per sample losses, right? So if I was doing CFAR 10 classification, each of these samples would be an image. And then, I would have a loss function, which is whether I made an error or not on that image, right? And and then my overall loss function will be the sum of my individual per sample losses. And of course, these losses depend on my parameters theta. And so I want to find a theta hat that minimizes the sum of losses. Okay, now, yeah, so we need a machine learning model which satisfies this. And most machine learning models nowadays satisfy this thing, right? Which is that the loss function is sum of per sample losses. The other requirement is that, well, I think that's the only requirement. Yeah, that we need to have a set of per sample losses, and the training is done by minimizing sum of losses. Okay, so here's in looking for prior work, we came across this quote by Legendre from like 2 centuries ago. And so what this says is that if among these errors there are some that appear too large, so he was talking about least squares or solving of linear equations, then those equations which produce these errors will be rejected, right, as they are deemed to come from faulty experiments. All right, so this essentially is our idea. It's about 2 centuries old. Right? I mean, we'll implement it in a slightly different way, but so okay. More specifically, there is quite a bit of work in classical statistics on the idea of trim loss. Okay, and that's essentially what that quote was referring to. So what trim loss is? Okay, so the standard approach, as I mentioned, to fitting a model to data, whether is to minimize the sum of losses over each of the samples, right? And so this is just a standard loss function. And trim loss is that do not try to fit all the samples because some of the samples are bad, right? So we should ignore them. And instead, we should fit only on the remaining samples. Okay, so the trim loss function is that you again find that the theta that minimizes something, but that something is not the sum of all losses, but it is the sum of, let's say, 80% of the losses. Right? And which 80% is also a parameter in the model which needs to be optimized. Right? So you first, so you kind of jointly do a set selection of which samples you want to care about, right? And then you minimize your loss function over that. Right? So in the CFAR10 image classification example, if we have a bunch of images and we don't believe all of them, and we have a current neural model, which we want to, if we have a bunch of parameters that we want to update, then, what this recommends is evaluate the loss on all those, you should minimize, the value of a model is not the sum of all its losses, but rather just the sum of its losses on the 80% of the samples where it does the best. Right? So, yeah, so that's the idea of trim loss. Any questions? Okay. It's a pretty simple idea, right? So the problem with it is that this is NP hard to do even for the simplest models, right? Even for linear regression, right? Like if each of these was a squared loss, right, of y minus theta x, and you have to minimize this over all the samples, and I allow you to choose only 80% samples to focus on, but then jointly optimize the S and the theta, that's NP hard, right? So we cannot really apply this, right? But it has great robustness property. Like if you could do this, you would have very good robustness property, right? This is what it would be for linear regression. So this is standard linear regression, right? Which is that you take a loss and you minimize that loss over all the samples. Trim loss is you have a set selection in between. Okay. And this is NP hard, right? So there's no hope of doing it for even more complicated models. Okay, so the simple idea is, and it's, as I said, at least 200 years old, is if we knew the good samples, we could get a good model, right? And if we knew a good model or a decent model, we could select samples that could maybe help it become better. Right? So you just split the trim loss idea. There's two minimizations. Just do them in alternation. So yeah, okay, so that's the idea. And we're going to apply this idea in two ways, right? As an outer loop and as an inner loop. Right? So if you remember the outer loop and inner loop I mentioned before, we're going to apply it in those two things. And we're going to talk about the outer loop before because it's conceptually easier to understand. Okay. So for the outer loop approach, we first initialize with all the data, right? So I take my good images and bad images, whatever images, and I just train a model like I used to do before, right? And I have this big drop in performance, but that's fine. Right? After that, I iteratively alternate between two things, right? I go back to my training data set, right? And I select all the samples that have the lowest current loss, right? So previously I never had a model and all my images were the same, right? But now I have a model theta hat, right? It's kind of inaccurate, but that's okay, right? But I have a model theta hat, and now I'm going to evaluate the loss of each of the training samples, right? And select the 80% that have the lowest loss, right? So my tau here is 0.8, right? And n is the number of training samples. Okay, right? So I'll pick the samples with the lowest current loss. I will throw away the remaining for now, right? I'm not throwing them away forever. I'm keeping them on the side, right? And then I retrain the model, right? Either from scratch or via fine tuning. So, let's forget about which way, right? But I train a model using this new set of samples. Okay. And then I can do this again. And I can do this again, right? So I can do a first step of sample selection now with the new theta hat, right? So I get a new set of samples and then I update again, right? So the first 20% that were kept aside the first time, are brought back in for the second time, for evaluation the second time, right? So I keep changing focus on which 80% I'm focusing on until I get to what I want. So each of these steps is very simple, right? The first step is just trivial sorting by the loss. Okay. And the second step is just standard model fitting, but on a subset of your training data. So, if you have a already set up like machine learning pipeline or something like that, right, then you need to make minimal changes to it. So that's another advantage of this approach. Okay, so it works for any, pretty much any model setting that has a loss function and a way to retrain the model. And so now for our results. So we have theory results and experimental results. The theory results are for simple machine learning models that we understand. And the experimental results are for big machine learning models that perform well in practice, but which we don't understand as well, right? So specifically, I'll be, our papers have theory results for a few simple models, mixed linear regression, Gaussian mixture models, and so on. But I'll be talking only about mixed linear regression in this talk. Okay, and I'll also present some experimental results afterwards. Okay, so what is mixed linear regression, right? So it's kind of a baby prototypical bad labels problem, right? So mixed linear regression is this. I have samples xi and yi, right? And if I had standard linear regression, then you would assume that that there is some underlying theta 1 star. And my data is the xy pairs where the y is generated as x theta star plus noise, right? So given a whole bunch of xy pairs, I want to find theta star. So that is simple linear regression. Mixed linear regression is a variant where you have 2 or more theta stars, right? And now every one of your samples comes either from theta 1 star or theta 2 star, but you don't know which one it comes from. Okay, so I have a bunch of red samples that that are well fit by a linear model theta 1 star, and a bunch of blue samples that are well fit by a different linear model theta 2 star, right? But now all the red and blue are mixed together, and you cannot see their color, and you're supposed to find out theta 1 star and theta 2 star. Okay, this is mixed linear regression. Okay, so where does this come up? So I first came across this problem as a simple model for, what happens, for example, in recommendation systems like Netflix. Many of you who have, who are sharing a Netflix account with family, which as per Netflix is 75% of its subscribers, then you have multiple people watching, right? And, you want to power different recommendations for different people, right? And if we did not have a profile selection step, right, then I would be getting recommendations based on what my kids watch, which is irritating, and my kids would get recommendations based on what I watched, which is not acceptable, right? So what we wanted, so this is an example where data is naturally mixed, right? And we need to unmix it to get a good prediction. And you can try to explicitly unmix by making profiles, but we are going to try to unmix it without these profiles. Okay, anyway, so back to mixed linear regression. We have a bunch of XY samples. They are red or blue, and we need to find the theta stars that they came from. Any questions about what mixed linear regression is? All right. Okay. So our approach is we're not going to try to explicitly. Okay. So this is the distillation of our approach to this problem. So first, I'll tell you what the distillation is, and then it'll kind of be obvious how it is a distillation, right? So the idea is we're not going to try to find multiple theta stars, right? That is what you would do if you were trying to develop a custom solution to this problem. We are not developing a custom solution to this problem. I already have my solution, right? Trim loss, right? And I just want to apply it to this problem. So what I'm going to do is I'm going to imagine that there is only one theta star, right? But that theta star does not explain all the data. Right? So I'm going to make it into a robustness problem instead of a mixed linear regression problem by imagining that there is only one theta star, right? But it's not going to explain all the data. And furthermore, I'm going to assume that I already know what either the exact fraction or the approximate fraction of samples that this theta star will satisfy. Okay, so typically, I am basically given the number 80%, right? So 80% of my samples are red. I know that there is a single theta star that well approximates this 80% of samples. I don't know which this 80% are, and I'm just going to try to find that theta star and not worry about any other theta star. Okay. So what is the process, right? So specialized to this problem, the process is exactly as before. I find the tau n samples that have the smallest, kind of iteratively in every step. I have a current theta. I find the 80% of the samples that have the smallest loss, and then I do least squares on those samples, and then I repeat. Okay, so it's the same approach, just applied to this baby problem. Okay, so this is what it looks like in, let's kind of get a pictorial understanding to get an intuition of what is happening, right? Like, why does this work? So let's say we have red points and blue points as before, and the red points are in the majority, right? And I'm going to try to find them. So my first step is to just do a least squares fit of the entire data set, right? So I just ignore color and I do least squares fit, right? And so when I do a least squares fit, I get, let's say, a line that looks like this. Okay, this minimizes the squared loss to all these samples. Now, what I'm going to do is I'm going to fix a number, let's say 80%, right? And then I'm going to trim the training data set. So what does that mean? I'm going to keep the 80% of the samples that are closest to this line, right? And the remaining 20%, I'm going to consider as being irrelevant to the theta star that I want to find. Okay, so I keep the 80% that are closest and I remove the 20% that are far, right? And I drop some reds and I drop some blues, but that's fine. Right, so once I do this, then I have a restricted training set, which is everything that falls between these two outside parallel lines, right? And now I'm going to refit my linear regression only to those points. Right? So once I do that, then, as you can see in this figure, right, that a lot of the points in this direction have been excluded from the new linear regression that I'm going to do, right? And hence the new optimum is a little bit closer to the underlying red direction. Why was it closer to the underlying red direction? Because in this thing that I excluded, a larger fraction of the blues got excluded as compared to reds. Right? The percentage of blues that got excluded was larger as compared to the fraction of the reds. And that is because reds were in the majority to begin with. Right? So my initial guess, while not being very close to red, was closer to red than it was to blue. Okay, and so more of the blues got excluded. And so at the next step, and so I fit on a better data set than what I had before. Right, and hence I got closer to the true red slope. Now I bring back all the things I kept aside for the first time, and I re-evaluate and again narrow down to only 80%. Right? So once I narrow down again to only 80%, I get this new band, and I keep only samples in that band. Right, and so now I have excluded even more blue samples. And I keep going. That's the algorithm, right? This is a picture of what this algorithm does for this simple problem of mixed linear regression. Okay, so here's the theorem, and I'm just going to state it informally, right? Which is that starting from any theta, so we kind of split, like for the theory, we split the two things. One is how do we initialize, and then what happens in every iteration. Okay, so first I'm going to present just what happens in every iteration, right? So if I start from some theta, right, then I will linearly converge to the closest theta star. Right? So if you remember in mixed linear regression, there are many theta stars, right? And now I pick a theta. Now that theta, theta 0, that is closest to one of them. I will not be able to converge to anybody else. I can only converge, if at all, right? I can only converge to the closest one, right? So that's the first thing, right? And even that may or may not happen, okay? Now, so what this theorem says is that I will converge to my closest theta star if a few things hold, right? What are those things? So the first thing, right, is that I'm running my algorithm with some estimate of what data is captured by this closest theta star. Right? So I have an initialization point. There is a closest theta star. I'm hoping to get there. Right? I need an estimate of what fraction of the data is captured by that theta star. Right? And so I'm running with 80%. Right? And so what this condition says is that the actual fraction of the fraction of the red points, the fraction of the data that this theta star represents, should be bigger than 80%. Right? If I'm running with 80%, but the closest theta star only explains 40% of the data, then I'm not going to be able to converge to it, right? Every time I slice it up, some red point, and then there will be a fraction of blue points that will remain because my slice is too thick. Okay? So it says that the true fraction should be bigger than the fraction that I'm running with in my algorithm, right? And then there are a few other conditions, okay? And the few other conditions can either be stated in a deterministic fashion, or it can be simplified for presentation for when the features are IID Gaussian. Right? So in our results, we have pretty detailed deterministic conditions for when we will get linear convergence to the closest theta star. Right? But in the interest of keeping it simple and accessible, I'm going to present what happens when these features are IID Gaussian. Okay, so which means the x's are kind of isotropic Gaussians, and the y's are generated with a corresponding theta star and x, right, plus plus. Okay, so for that setting, right, so if we have a theta hat in this current iteration, that is closest to theta star 1, which is the first component, right, which means it is closest in Euclidean distance. Right, and if the fraction is larger than the true fraction tau 1 star is bigger than the fraction of 80% that I'm running with in my algorithm, then the next iterate, right, will satisfy, which I'm going to call theta hat plus, right? So that's the next step of my algorithm, right? Will be a constant fraction closer than what I was before. Right? So this is basically linear convergence to a noise ball. And for this to happen, I need enough new sample, like enough samples in my data set, right? So the number of samples in my data set should be bigger than the dimension D divided by tau raised to 4 and C squared. Right? So C is this fraction. I want C to be small because that means I'm making quick progress. But if I want to make quick progress, I need a lot of samples, right? Also, as you can imagine, the problem gets harder as the number of samples that, the fraction of samples that are chosen at every point goes down, right? And that's what the tau raised to 4 is. Okay. So this is a self-contained simple theorem for the case when the x's are Gaussian. Right? But when the x's are not Gaussian, then you need to explicitly deal with what happens if you have batch singular values in the x's covariance matrix and so on. Any questions?
I have a question. So you I guess italicizes that the samples, you need these many fresh samples in that iteration. So in practice, you would just sample split, or do you think that the sample splitting is just for the theory but not needed in practice?
Yeah, exactly. The sample split is only for the theory. It's not needed in practice, right? So the problem is that Okay, so what Christina is asking is, so let me just clarify. What this fresh means is that what this theorem is for is that I have a training set and I split it up into many different, let's call them meta sets. And then I do theta hat on meta set 1, but then I go to meta set 2 and I never come to meta set 1. Right? So I'm using fresh samples at every time. And the reason I do this is because that makes it easier to analyze, right? So specifically, since this is not the deterministic case, but is Gaussian, I'm assuming that the x's are independent of the theta that I have currently, right? But now if I go over the training data once and I make a theta, right, then that assumption is no longer true, right? All those x's are dependent on theta, right? So that makes it inconvenient to make a good theorem, right? And so I need to use fresh samples to have a theoretical result. Right now, our deterministic result is exactly that, right? Like it doesn't have this issue. Yeah, good call out. Any other questions?
Sujay, I have a question. This is Rahul Vaze.
Yeah.
So when you say theta hat is closest to theta 1 star, among what classes of theta are you looking at the minimizer? So theta 1 star takes values in what? Because it could essentially be the left-hand side on the minimization could effectively be 0, right? So you're restricting your class of theta 1 somehow.
Yeah, okay, good question. So the theta ones, so these theta stars are my true underlying components, right? So for example, if this was my data set, then, there is some line here, which is the line that blues were generated from, and that's theta 2 star. And then there is some line here, which is where the reds were generated from, and that's theta 1 star, right? So in this case, there are only two possible values of theta star, which is theta star 1 and theta star 2, right? They're the two underlying components of the mixed linear regression problem, right? And what the assumption says is that my original theta hat, let's say my theta hat is a slope like this, right, is closer to theta 1 star, which is the red slope, as compared to the theta 2 star, which is the blue slope.
So, and how do you ensure that such a thing happens? Like, is there any guarantee of any probabilistic guarantee on the initial choice being closer to one and not the other?
Yeah, good question. So that is not a part of my theorem, right? So my theorem just says that if you are closer to theta 1 star, then you will get to theta 1 star, right? Now, you do need a way to get, to get to that initial point, right? And so the answer to that kind of depends on the problem. So for example, if you were in a setting where there were two theta 1 star and theta 2 star, and they were both unit norm, and we had random Gaussian x's, and 80% of the y's came from theta 1 star, and 20% of the y's came from theta 2 star, right? So we have 80% red points and 20% blue points, and everything is nice and well conditioned. Then in this case, if you just do least squares on the entire data set to begin with, it will satisfy this, it will satisfy this condition.
So I have one comment, if time permits, that suppose you're running your algorithm, after a few iterations, you're very likely to be closer to theta 1 star compared to theta 2 star. Why not restart your algorithm at that point?
Restart, oh, you mean like, but we are effectively kind of restarting it in every iteration, right? Because we are reconsidering the entire data set.
Right, so that
data and finding the lowest loss.
Correct. Then theta hat being closer to theta 1 star should effectively, as time progresses, will be more and more likely, essentially.
Yes, exactly, right? Yeah. So that's absolutely true. It'll get closer and closer. That's what this theorem is stating.
Thanks. Yeah.
Okay. Any other questions? Okay. How much time do I have left?
You have 15 minutes.
15 minutes. Okay.
I guess including a little bit of time for questions at the end.
Yes. Okay. Yeah. So this is the theorem, so the way you can apply the theorem if you want to actually solve the mixed linear regression problem per se, right, is to peel and repeat, right? So first somehow get to theta 1 star, which is the red points. So let's say, for example, we had red points, blue points, and green points, and yellow points, right? Then first, hopefully we can remove the blue points because they are the most in the data. Oh, sorry, red, whatever, right? We remove the color that's most in the data, right? And then we find the points that are best fit by the theta star I learned and just remove them from the data set once and for all, right? And then repeat again and repeat again, right? So you can iteratively peel, right? So in one of our papers, we analyze this iterative peeling procedure for mixed linear regression. And we show that we get state-of-the-art statistical performance for this problem, right? So even though we have this kind of off-the-shelf solution, which is not specifically made for mixed linear regression, we can show that we match the current statistical bounds for mixed linear regression, as shown by any other method, under the case of Gaussians with fresh samples. Okay, so I'm now going to switch to showing some empirical results, right? And so, pretty much any machine learning talk nowadays has to answer this question. Okay, that all is great, but what about deep learning? I care about deep learning. I don't care about theoretical guarantees for mixed linear regression. And so, okay, fair enough. Kind of deep learning was our motivation anyway, in the sense of trying to develop a method that is generic enough to be applied across a more generic machine learning modeling framework, right? So one issue immediately, right, and which is now already well known, is that deep neural nets have a tremendous amount of representative power, and you can essentially train them to zero training loss on every single training sample, right? So as opposed to linear regression before, where I could, where I actually had a loss, right, for every training sample, which I could then sort by and choose. Now, this is not true anymore, right? Like if I train neural networks to convergence, then as has been noted in many settings, the training loss will be zero for all samples, right? So it's perfectly fit the data, right? And so there is no way to slack, right? So then we had to change how we apply this a little bit. And basically the change we made is that we run the machine learning training only, like, not to convergence, but we kind of stop before convergence, right? While there is still a loss. Okay. So that's what this title says, that initial epochs of training can differentiate. Okay, they at least give a loss for every sample. It's not zero, right? And furthermore, those losses are indicative of good or bad. Okay. So, if you have systematic error labels, which is the the CFAR 10 images with labels, and some labels are wrong in a systematic way, right? Then what this plots is as a function of the number of epochs of training and the accuracy of the model, right? And so we see that, and then I've split it out by what are actually correct samples and what are wrong samples, right? So in these initial epochs, we just have a standard way to train, which is that we don't account for good and bad. We just train it on the bad data set. And the model we get, we keep evaluating it on the training data set it was trained on, right? And then after, I guess, one epoch, we have 40% error on the clean samples and 40% accuracy on the clean samples and 20% accuracy on the bad samples, right? Which have bad labels, right? And as this number of epochs goes further, the accuracy improves for both the clean samples and the bad samples, right? But there remains a difference. So we could have stopped these epochs at some point and done a selection. And when we do a selection, we will boost the number of clean samples. Okay, that's what this plot indicates. And it's the same for if you have a generative model, and so on. Right? So this is a kind of little modification that we have to do to our algorithm to apply it to a deep neural network setting. Okay, so once we have that, then we have iterative trim loss minimization for deep image classification. where we iterate between choosing the best fraction of samples after an initial epoch and retrain only on those samples. Right? So this also has the advantage of not wasting computation and going through several epochs for a training set that you're going to throw away anyway. And so essentially what this table shows is that we recover the accuracy of what the model had when there was no systematic errors in labels, right? So on the, let's say the CFAR10 data set, right, when you have 60% of the samples being good, right, and as an algorithm designer, know this number 60%, right? So, and I choose my tau to be less than 60%, and then I run my algorithm for several loops, right? Then the baseline performance, if I didn't do all this fanciness, would be 64% accuracy, right? The oracle, which is trained only on the good set, right? So the oracle knows which samples are bad and it removes them, and it's trained only on the good set, that gets like 90% accuracy, right? And our model gets 75% accuracy, right? So it significantly improves over the 65%, but obviously it doesn't get to 9%, right? On the other, and so this kind of holds true for like as long as the number of good samples does reasonably outnumber the number of bad samples.
Sujay, how did you generate bad samples?
Oh, so it's the systematic error in labels, which means that so let's say, so what does 60% mean? 60% means that I take, let's say automobile is one of the labels in CFAR10, then I take 40% of automobiles and call all of them horses, right? And I take 40% of horses and call all of them birds, and so on, right? So it's a systematic error label model.
Okay, thanks.
Okay. Any other questions? Okay. So that was for image classification. Now, what do we do for the density modeling setup, which is where I showed the results from the output of a GAN for the MNIST handwritten images, right? So we were making false handwritten image, or like kind of generated handwritten images by training a small GAN on MNIST, right, with bad data. So the way GANs are trained is, okay, so this is the generator, right? This is what I want, which is I give a random vector and it generates handwritten, something that looks like a handwritten digit, right? So the way this is trained, I mean, one of the ways, there are many ways nowadays, but let's, one of the ways this is trained is to have a generator to make this thing, and then to have a different network called the discriminator, right? And to think of this as like a game between the generator and the discriminator. What the generator is trying to do is to make nicer and nicer images of things that look like handwritten digits. And what the discriminator is trying to do is, given a digit, trying to label it as being real or generated, right? So the discriminator is trying to call out the generator, and they are both trained together, right? So now you have a training data set of real images, and then you keep generating these things, and initially they look like garbage, right? But then the discriminator is easily calling them out, and as a result, the generator network starts improving, and soon you get pretty good results which start fooling the discriminator. Okay. So here the model weights theta are the weights of both the generator and the discriminator, right? So to apply our idea to the GAN framework, we need theta to be the model parameters of both. Okay. And the training data set is what we think of as real images, right? Now, of course, in our setting, our real images itself are, have 20% junk, right? And so now, but we're going to still apply the same framework, right? And we don't know which 20% are bad. So this is what caused that problem that I showed before, right? When 20% of them are bad and we just train it in the usual way, right? Then we get some pretty bad looking output, which is a mix of handwritten digits and pixelated fashion accessories. Right? So how do we apply our idea to this framework, right? So the way we apply our idea is that if you think of only the generator in isolation, then we don't really have a loss function, right? We only have a loss function when we also think of the discriminator, right? And so the idea is to use the output of the discriminator as a loss, right? So which means that, so the algorithm is this, right? I train my GAN with all samples, right? Just as I would do if I didn't have any bad data, right? I just train it on all the samples, but run it only for a few epochs, right? And then I take the discriminator, okay? Leave the generator aside for a bit, take the discriminator. What is the discriminator? It's a classifier which tells me if my training data image, any image is real or fake, right? And I take that and I apply it to my training data set, right? So it has been trained assuming the entire training data set is great, but now I go back and evaluate it, right? And I apply my discriminator on my entire training data set, and I keep the 80% that best fit the discriminator, for which the discriminator is most sure that these are actually real images. All right, so that's how I filter my training set. And then I train again for a few more epochs, but starting from where I left off before, right? So I'm not starting from scratch. Right? Yeah. So is that clear? Any questions?
Do you retrain both the discriminator as well as the generative model?
Yes, both. So theta is always both. Yeah. So if I don't retain the discriminator, it will always pick out the same samples again, right? So I need to change that as well. Okay. All right. Yeah. So qualitatively, we can see this is what happens. When you have a 20% fashion MNIST corrupting 80% MNIST, right? Which is that this is the baseline. This is what I showed before. And then, this is after, one iteration of our algorithm. This is after 3 iterations. This is after 5 iterations, right? So it does manage to at least filter out pixelated fashion MNIST images and, keeps the handwritten images, right? So for those of you who work on mode collapse, what we are essentially trying to do is to select which modes to collapse, right? And we are trying to collapse the bad modes, which correspond to fashion MNIST. Okay, in the interest of time, okay, so just a quick note, this doesn't always work, right? So in this case, when I have 60% good data and 40% bad data, our algorithm fails, right? So even though it is the majority, it's not enough to just be the majority, right? It needs to be a little bit more than the majority. Okay, let's see. I have 1 more minute. Okay, so I'll just maybe skip the inner loop approach, although I think it's interesting, but it'll take a lot of time, and go to some, kind of brief open questions, right? So I think one interesting question has to do with the interaction between robustness and boosting. Okay, so for those of you who don't know what boosting is the method to make a strong classifier from weak classifiers, right? So, if all you could do is build a decision tree, and even that decision tree is not so great, it only gives like 60% accuracy, right? Can you learn many decision trees and combine their outputs to get 100% accuracy, at least on your training data, right? So boosting lets you do that. Right? It's a pretty standard, it's a very old technique, right? And what boosting does is it estimates a model from weighted samples. Then after it does that, it goes to the training samples. But now what it does is it gives a higher weight to samples that have a high loss, right? So if I'm learning a bunch of models one after the other, right? Then I will first fit my model to a bunch of samples. Then I will give more weight to samples where I made an error. And then I'll fit those. And then I'll give more weight to samples I made an error, and then I'll fit those, and so on, right? So it's kind of doing like what we are doing, except that it's the exact opposite, right? It's learning a sequence of models, but it is giving more and more weight to samples that have a high loss, right? And what boosting allows you to do is to get very good training accuracy from very bad models, right? Like I have a decision tree that gives like, 60% accuracy, I can combine, I can learn a bunch of them in a sequential way, and I can get 100% accuracy on my training data. Right? So that's boosting. Doesn't say anything about robustness. Right now, what we have done is we have shown that the opposite of this procedure, which is to focus on the low loss samples, right, has very good robustness properties when you learn a sequence of models. Right? And so I think a good intellectual question is that are these two opposites of each other and we can never get both? Or is it actually possible to do boosting when there is bad samples? Right? So I think that's a very interesting question. If anybody wants to think about it, I'm happy to discuss. Okay, so this brings us to the end of my talk. So basically what we saw is that selecting samples based on the lowest current loss is a good kind of generic way to get robustness across several different settings. It gives state-of-the-art results for mixed linear regression. It gives some decent results for Gaussian mixture models. And it also has decent empirical performance on kind of small and moderate size image tasks, which is what we evaluated on. So I think that's it. We'll stop here in the interest of time, and happy to take questions.
Thanks, Sujay. So we will take questions in just a moment. I want to make one announcement about the seminar series. So we will not have the SNAPP seminar next week due to the election. And 2 weeks from now, we are very excited to co-host the Markov lecture together with Informs APS. And so they will be, again, at the same time, the same Zoom link. And our speaker this year for the Markov lecture is Sam Forrest. And the discussant is, okay, and the information will be forwarded in the email. I'm just gonna look it up. Okay, so now I'll be happy to, well, Sujay can take questions, and if you want to post questions in the chat, you're welcome to do that as well. But you can also feel free to just unmute yourself.
I have a question.
Yeah.
Thanks, Sujay, for an awesome talk. So my question is about the choice of that parameter tau, the fraction of good samples. So I understand that the true good fraction of good samples has to be greater than tau for things to work. But what if tau is so small that the true good samples is much greater than tau? How does that affect the algorithm?
Oh, so I see. So it's like the theta star you're after, is good for 90% of the data, but you're being conservative and your algorithm only has tau at 30%.
Yeah.
So it should not change. You will need a lot more samples, and you might, you might be leaving a lot, something on the table in the sense of, you may not be able to converge to the right place, even though you could have if you just were not, right? So that's kind of a little bit answered. Okay, empirically, it's answered by something like this, right? Like if I had 80% of my data, but I imagine it was 60% and shows a very like small tau, I may very well end up with something that never recovers from the initial bad data, right? Just because of noise.
I see.
Right.
Thanks. So it is somewhat sensitive to that.
I think it is sensitive when you have noise. So if you think of mixed linear regression, if you had no noise, then what you're saying will be just great. It'll be fine, right? It won't matter. But the moment we have noise, then it's a question of like, what amount of noise can your, like that's something I didn't discuss in this talk, but there's also a parameter of how much noise there is as compared to the X, right? Like the SNR, right? And so if the SNR is low, right, then your algorithm is being conservative will actually not, may not converge to it.
Thanks.
Hi, I have a question. Is your algorithm is required to know the percentage of error samples, a bad sample prior to the algorithm?
That's right. Yes. Yeah. So that is an issue, right? Like we need to know, or we need to have an estimate And, we can try to be conservative, so as to, okay, so first of all, for, empirically, for initialization, right, like the first step, to even be any good, like if our first step is not any good, there's no hope to improve. For the first step to be any good, there should be the amount of good data should be in a decent majority, right? And once it's the decent majority, then it's a question of, how to choose our tau for the algorithm, right? Should it be 60%? Should it be 70%, 80%, right? So, I mean, at that point, and, that is back to the question that, we just answered, right? Which is that if you're too conservative, you may leave a lot on the table, right? So one empirical answer could be try it out at different levels and see what happens, right? Like, try out 60%, 70%, 80% in parallel, right? And, see if you're getting good output. But as far as that theory is concerned, we need to know tau.
Thank you.
Hi, Sujay. This is Seung again. Hey. So robust mean estimation is very well understood. You could apply your algorithm to robust mean estimation with the L2 loss.
Yeah.
So how do the guarantees compare?
Okay, so let's say robust mean estimation for a mixture of Gaussians, suppose.
Single Gaussian, even simpler case. Single Gaussian with outliers.
Single Gaussian outliers. Okay, so if the so my feeling is that this algorithm could be pretty bad. Okay, specifically, because typically the standard setup, if I understand for robust mean estimation, is that you have Gaussians, and then the outliers are adversarially placed, either by just knowing the distribution or by actually knowing the realized points, right? So the mapping to my setting is that is an error in features situation, right? Where the axis doesn't have an error, right? And if you notice the things I talked about, there are no errors in features. I think my algorithm will be pretty bad when there are errors in features, right? Which is why it's also not good for like adversarial training, where people put like, change a few pixels and, make machine learning models misclassify. That's also an error in features problem. So I think for both of these, this is not a good approach.
And also what I guess the point I wanted to ask is, if the adversary can place arbitrary examples in, then you could make your algorithm fail, it seems like. It could, right? I could fool your algorithms to go after those.
Yes. Yeah. So, like, if you put in like bad, Sevung images, right, then there's no hope, right? But if all you can do is change labels but not touch the images, then there is some hope.
Got it. Thank you very much. Oh, can I ask one more question?
Yeah.
Okay. So for mixed linear regression, there are different settings though, right? Depending on what you assume about theta star 1, theta star 2, theta star 3. If you don't assume much more than their distance is separated apart, then there's an exponential square root of k gap and the sample complexity with k centers.
Mm-hmm. Yeah.
Whereas, I guess, do you need spectral gap also, which in the thetas? Stars?
Right. So there are two parts to my result, right? One is that we are already magically close to something, and then we have to get closer, right? So there we need the spectral gap only as compared to the amount of noise, right? So we have y equal to x theta star plus noise, right? And we need a spectral gap there because of the noise, right? But the bigger place where the spectral gap thing comes up is in the initialization step, because there we're actually using all the data, right? So if you want to initialize by just doing least squares on all the data, right, then if the thetas are very close to each other, which is when, which is the batch situation, we will not be able to get close to one of them.
Well, I guess they're not just close, but like theta 2 star was like 10 times theta 1 star.
Oh,
so
yeah. Okay. Right. So that is outside our assumptions. We assume all of them are on the unit ball.
Right. So they could create problems.
That could create a problem. Yeah. Because the squared loss is not comparable in terms of scale.
Thank you very much. It's
Yeah,
great
yeah.
talk.
And, just to follow up, like there's a variant of our algorithm which, instead of looking at the level of the loss, looks at the norm of the gradient, and that may be able to correct for something like this, but even that is not certain.
Thank you so much.
Any other questions? Okay, well, there are no more questions.
Thanks, Sujay.
Yeah. Okay. Yeah. Thank
Really
you.
enjoyed the talk, and we'll see you all here 2 weeks from now.
Yeah. Thank you, everybody.
Thank you, Sujay.